Hi, in this video, we will consider a few examples of 3x3 systems with unique eigenvalues and eigenvectors, and consider how to also handle these kind of questions. From the matrices above, we can see that we have different matrix representation. Now, some of them are upper triangular, some of them are lower triangular. We will consider all these things so that we can best prepare when we meet such questions. Taking a look at the matrices above, if we consider the matrix B, we see that it is upper triangular. If we consider matrix D, we see it is lower triangular. Also, matrix F is also upper triangular. All these kinds of matrices simplify your calculations. Considering matrix B, we have we have 2, 3, 0, 0, 0. We have -1, 0, 0, -1. Usually, when we are given a matrix, we start with finding the determinant of the matrix minus lambda I, and we equate it to 0. This is the same as equating the polynomial to 0. So if the polynomial equals to 0, then the determinant of b minus lambda I will be equal to 0. But in this case, because our matrix has been simplified into upper triangular, our eigenvalues lie on the diagonal. So our eigenvalue for the matrix B are lambda 1 equals 2, lambda 2 equals -1. Lambda 3 also will be equal to -1. So we see that -1 is repeated twice. Now, if we have a case where all the lambdas are repeated, that is lambda 1 is equal to lambda 2 is equal to lambda 3, then we say that the algebraic multiplicity equal to the geometric multiplicity. And if we have, let's lambda 1 to be equal to lambda 2, but they are not equal to lambda 3, then the algebraic multiplicity would not be equal to the geometric multiplicity. The algebraic multiplicity, geometric multiplicity. Okay, in this case, this falls under the second category. So we have I and II. If lambda 1 is not equal to lambda 2, which is also not equal to lambda 3, we have the distinct eigenvalues. So we've already taken a look at an example of a distinct eigenvalues. So we consider now the eigenvalues with either every one of them being equal, or eigenvalues with some of them being equal. After we find our eigenvalues, the next thing we need to find are our eigenvectors. And after finding our eigenvectors, we group them into the stable subspace, unstable subspace, and the center subspace, if there is any. This will lead us to determine our P and P inverse. After doing that, we will write down our diagonal, which is equal to P inverse AP. In this case, since we have some of the eigenvalues being equal or all the eigenvalues being equal, we have to take a step further. So instead of determining this expression, we will rather determine this expression, P inverse SP. We will have this to be given because we have determined our eigenvalues by then. We would have found P inverse because we would have found P. So the only thing that we'll need to look for will be our S matrix. So in this case, our S matrix will be P times the diagonal P inverse. After finding the S matrix, we will now find an N matrix. This is what is actually going on. Our matrix, which was given, was divided into two matrices. We had the S plus N matrix. Now, in order to find A, we need to find S plus N. The S matrix we are looking for will be placed here, and the N matrix, which is the nilpotent matrix, is what we will find next. So our solution will look a little bit different from the usual one that we had. The usual one that we had previously was given by x of t to be equal to e raised to the power, considering A to be the matrix, t x naught. Now, since A has been broken into two matrices, it implies the matrices are commutative. We have e to the power s plus n multiplied by t x naught. So with this we have e to the power s t e to the power n t x naught, and we expand e to the power n t using the Taylor series expansion. Our solution, which is x of t to be equal to p s p inverse multiplied by I plus n t plus n squared t squared divided by 2 factorial plus n cubed t cubed divided by 3 factorial multiplied by x naught. So we're using the lambdas, lambda 1 to be equal to 2, lambda 2 and 3, which is equal to minus 1. We can now find our eigenvectors. B minus lambda I V to be equal to 0. We have 2, 3, 0, 0, minus 1, 0, 0, 0, minus 1. Minus our lambda 1 is 2, so we have 2, 0, 0, 0, 2, 0, 0, 0, 2. All these multiplied by our vectors x, y, and z equal to 0, 0, 0. Simplifying, we'll have 0, 3, 0, 0, minus 3, 0, 0, 0, minus 3. Multiplied by x, y, and z, which is equal to 0, 0, 0. So from this expression, we can have 3y to be equal to 0, which implies y equals 0, and minus 3z, which is equal to 0. So we have z to be equal to 0. But we don't have any expression which contains x, so we write let x to be equal to t. So our v1 will be given by x, which is given by t, y, which is 0, and z, which is also 0. Factorizing t, we'll have t into bracket 1, 0, 0. Our v1 can be written as 1, 0, 0. Since lambda 2 and lambda 3 are the same, we have a special way to find them. We have b minus lambda 2I times the vector v equals 0. We have 2, 3, 0, 0, 0, minus 1, 0, 0, 0, minus 1. Minus 1, 0, 0, 0, minus 1, 0, 0, 0, minus 1. Multiplied by x, y, and z is equal to 0, 0, 0. Simplifying will give us 3, 3, 0, 0, 0, 0, 0, 0, 0. Multiplied by our x, y, and z is equal to 0, 0, 0. Now here we can write 3x plus 3y to equal to 0. Multiplying through by 1 over 3, we'll have x plus y to be equal to 0. And this implies that x is equal to minus y. Dividing y by x, we will get minus 1 over 1. So if y is equal to minus 1, then x is equal to 1. So we have one of our eigenvectors to be equal to, so let's say v2 is equal to 1 minus 1, 0. To find v3, we square this expression. So we have b minus lambda 2I all squared multiplied by v to be equal to 0. So squaring this expression, we had 3, 3, 0, 0, 0, 0, 0, 0, 0. We have 3, 3, 0, 0, 0, 0, 0, 0, 0. So this is b minus lambda 2I multiplied by b minus lambda 2I. We will first find the square of the matrix, and then we will substitute and find the vector, which is v3. We have 9, 0, 0, 0, 0, 0, 0. 9 and 0. This gives us 9, 9, 0, 0, 0, 0, 0, 0, 0. Multiplied by x, y, and z. It gives us 0, 0, 0. So we have 9x plus 9y to be equal to 0. Multiplying through by 1 over 9, we have x plus y to be equal to 0. It's x equal to minus y. Now we see that this expression is the same as the one we had previously. We cannot use the same solution as the previous one. If we do that, our p-matrix will not be linearly independent. The main aim for finding our p is to get a linearly independent matrix. We see that we have x is equal to minus y, which is the same thing as what we had earlier. In this case, you will just look for the component of the vector for which you do not have a value assigned to. So we say that z is the component that we haven't assigned any value to. You will set z to be equal to t. Now, your v3 will be given by, since we are ignoring the first two components and we are only taking z, we will have 0, 0, t. And now we are going to have t bracket 0, 0, 1. Whenever you determine a solution for repeated eigenvalues with 1 which is not part of the repeated, so let's say lambda 1 is equal to lambda 2 but not equal to lambda 3, you can do this step. If your solution keeps repeating, that means you keep getting the same solution, it is best to employ this method. So our v3 is given by 0, 0, 1. Now to write down our p, we know that our p is just a matrix containing the eigenvectors. So we have v1, v2, and v3, which is given by, we know v3, which is 0, 0, 1, and our v2 was given by 1, minus 1, 0. Our v1 is given by 1, 0, 0. Now we will find our p inverse by finding the inverse of the determinant of p multiplied by the adjoint of p. And we already know how to find the adjoint of p. So to find the adjoint of p, it is given by writing all the elements of p, 1, 0, 0, 1, minus 1, 0, 0, 0, 1. You repeat this column and this column here and here respectively. So we have 1, 0, 0 for this column and 1 minus 1, 0 for this column. Now you select this row and this row and you write them down here and here. So this row for the elements here and this row for the elements here. We have 1, 1, 0, 1, 1, 0, minus 1, 0, 0, minus 1. Now you cross these elements out and then you do your 2 by 2 multiplication. So to get our matrix, find the determinant of this and this. We have minus 1 times 1 minus 0 times 0. So we have minus 1. We find the determinant of this and this. So we have 0 times 0 minus 1 times 1. We have minus 1 again. Find the determinant of this and this. We have 0. We find the determinant of this and this. We have 0 again. Determinant of this and this, we have 1. Determinant of this and this, we have 0. Determinant of this and this, we have 0. Determinant of this and this, 0 again. Determinant of this and this gives us minus 1. So we now find the determinant of p, which is given by 1 into bracket minus 1 times 1, so minus 1 times 1 minus 0 times 0 minus, we have 1 into bracket, so we have 0 times 1 times 0 times 0. Okay, So 0 times 1 minus 0 times 0. And the last one is just plus 0. So with this, we have 1 multiplied by what? Minus 1, which will give us minus 1. So our P inverse is given by 1 over minus 1 is just minus 1 multiplied by the adjoint that we have here. So we have minus 1, 0, 0. We have minus 1, 1, 0. And we have 0, 0, minus 1. Now, multiplying by minus 1, we have 1, 0, 0, 1, minus 1, 0, 0, 0, 1. So this is our P inverse. Now, we've found our eigenvalues, the diagonal, our eigenvectors P and P inverse. Your E of T is given by E raised to the power of the diagonal of the elements of the diagonal, which is lambda 1. So we have lambda 1, lambda 2, and lambda 3 multiplied by T. And this is equal to E raised to the power, the first eigenvalue was 2, so 2t, 0, 0, then 0, e raised to the power minus t, 0, 0, 0, e raised to the power minus t. Now, we also have to find our S. As I said, our S is given by P, D, P inverse. Okay, so our P, which is 1, 0, 0, 1 minus 1, 0, 0, 0, 1. Our D, which is given by 2, 0, 0, 0 minus 1, 0, 0, 0 minus 1. And our P inverse, which is also given by 1, 0, 0, 1 minus 1, 0, 0, 0, 1. I think that's what we have. So next, we just do the multiplication because we need a value for our n. So we have 1, 0, 0 here, 1 minus 1, 0, 0, 0, 1. And this will give us 2, 2, 0, 0, 1, 0, 0, 0, minus 1. We have 2, 3, 3, 0, minus 1, 0, 0, 0, minus 1. So this is our S. Now we are going to find our N, which is given by E minus S. Our A is given by 2, 3, 0, 0, minus 1, 0, 0, 0, minus 1. Minus our S, which is also given by 2, 3, 0, 0, minus 1, 0, 0, 0, minus 1. And this, we'll see that the resultant will be 0, 0, 0, 0, 0, 0, 0, 0, 0. So in this case, there's no value for n. Now, our solution, x of t, is given by e raised to the power b t x naught, which is expressed as p e of t p inverse multiplied by I plus n t plus n squared t squared divided by 2 factorial times x naught. Substituting, we have our x of t to be equal to our p is given by 1, 0, 0, 1 minus 1, 0, 0, 0, 1. Our e of t is given by e raised to the power 2t, 0, 0, 0, e raised to the power minus t, 0, 0, 0, e raised to the power minus t. And finally, our p inverse is given by, it's also 1, 0, 0, 1 minus 1, 0, 0, 0, 1. And now we see that our n was 0. So if you square n, you still get 0. If you cube it, you still get 0. So our only value to write here is I multiplied by x naught. Multiplying everything here by I doesn't actually change it. So we still have our x of t to be equal to 1, 0, 0, 1 minus 1, 0, 0, 0, 1 multiplied by the value here, e to the power 2t, 0, 0, 0, e to the power t, 0, minus t, sorry, 0, 0, e to the power minus t. Then we have 1, 0, 0, 1 minus 1, 0, 0, 0, 1 multiplied by x naught. So you can do the calculation and simplify this